Okay, good morning. If you look at our class schedule, okay, the first thing I should remind you is next Tuesday is our midterm exam. So you should prepare well, like we said. Likely, I would encourage you to prepare some, like one sheet of the reference. I think you can go over all the things we covered until the end of Thursday. Okay, so then we will cover, actually, you probably also see, originally I put a chapter 3 text mining here. I actually completely shifted text mining after the midterm exam. It simply says for the whole first half, we will only cover the network mining part. That means we cover the first chapter is on introduction to networks. The second chapter is mining heterogeneous information networks. I actually add another set of slides, say part 2. So we will finish this lecture. We are going to finish part 1. Then next lecture we are going to finish part 2. At least we finish part 2, no matter how far it goes, we probably will stop in front of the midterm exam. Then after exam, we are going to start the text mining part. Okay. So that's the arrangement. Hopefully you know the coverage of the midterm exam. Another thing I should remind everyone is we tend to give you 90 minutes for the midterm exam. That requires you to come likely 10 minutes earlier, so we can start 10 minutes earlier because we want to finish exactly 90 minutes. We leave another 10 minutes for the next lecture they can get in. Okay, so that's the reason I probably should announce again. The next Tuesday, the midterm exam, we will start at 9:20. You can see here, midterm starts at 9:20 and ends at 10:50. Okay, so total 90 minutes. Is that clear? So just next Tuesday, you prepare to come here earlier. Okay. So that's about a midterm exam. A sample exam is already here. You click the button, you will be able to download 2013 midterm exam, but not 2016. Okay. Now we are going to continue our discussion on our prediction analysis. Like last time we mentioned, we want to use heterogeneous information network to predict something may happen, some higher probability we can do some good prediction. Okay. Here we say we want to predict the future co-authors. That means based on the current author and all the years, you try to predict the future years. And co-author relationship essentially is APA. They share a common paper. So that's a link, APA. You try to predict this APA link. You're based on all the other links in your heterogeneous information networks. And you probably can see we list almost all the length 3 and length 4 heterogeneous information networks paths related to this A to A. That means related to co-author. You want to predict the co-author. We look at the two ends of the authors, try to see what other factors may impact these co-authors. Okay, that means we want to see whether the citation, you cite the other papers, whether you're going to co-author with the authors, or other papers cite your paper, whether you will become co-authors, or whether they share common venue, common author, common term, or common citations. Okay. And this one means if you cite the other paper cite another paper, whether you will be the co-author of the other papers. Okay. This is cited by. Okay. If you your paper side by another paper, that paper was side by another paper, whether you become the co-authors. Okay, and this one is if a paper cite both of the two authors, in the same paper, whether these two authors will become co-authors. Okay, so you can see these are all reasonable meta paths you can use to do prediction. And we need to set up a model. Essentially, it's a training model. You take all the data you have, and you try to see which meta paths will really play a role. Okay, will really play a role. You can think in this way. You'll see, like you got two authors, Mike and Ann. Suppose in the future they become co-authors. Okay, then you want to see what are their existing paths. For example, whether they have common co-authors. Maybe they have 4 papers, 4 paths which they have common co-authors, or common co-values, or common co-terms. You probably can see they share lots of terms. And whether you cite the other paper, whether this is citation authors. So you can see these are the facts. This is whether they become co-author or not. But another one, like Mike and Jim, you probably see they do not have co-author relationship. Then you check their relationship, you see which one likely will give you the prediction. Okay. You can put those whole thing into a regression model. Okay. Currently, actually in the paper, it uses logistic regression model. Essentially, is based on these logistic regression formula. Okay. Then you try to compute the maximum likelihood. Okay, you can estimate the maximum likelihood using this formula. But I'm not going to give you the detail because this, if you do not really know it, you think this is obvious. But you do not know it. This is part of a statistics course on the logistic regression. Yes. Yeah, actually, that's a good question. That means, for example, here they say Mike and Ann. The question is whether when we do the training, we just consider start with Mike. Actually, the training, when we do the training, we do not even know what kind of query you're going to ask. To that extent, you are using all the authors and try to see their collective behaviors. That means you are thinking every pair you can find in your database. Okay, you try to do the training to see what are the factors which impact these people later become co-authors. Okay, you can think this is the fact you already know. In a few years they become co-authors, but these are the things you find in your database. Then you try to see what are the important factors. For example, whether this co-term is very important, or whether this co-value is very important. You try to see these things. Then, using this logistic regression, you are going to get a weight of every metapath. Okay, so that's a general philosophy. Okay, but we are not going to get into the very detailed formula because that's essentially it's a logistic regression model. It's a training model. Then how do you calculate those measures? You still have many ways to calculate measures. There's one way is you use pass count. That means how many paths going through those ones. Another one is normalized pass count. Normalized pass count means you look at the current following this path R. Okay, this is following the reverse path R. That means that you think about it. These two co-authors are symmetric in the sense you just check this part and check this side, okay? Because remember, the citation is not symmetric. But once you want to find the two co-authors, like Mike and Ann, actually, my co-author with Ann means Ann co-author with Mike, right? So to that extent, you have to check both sides, okay? So you can see this is R, this is reverse path of the R. And here is you want to look at these two, AI and AJ, AJ and AI here. And this one says from AI to anywhere. Okay, this is from anywhere to AJ. So this essentially is you try to normalize it. Okay, normalize it means I just look at AI, AJ, but the denominator is AI can go anywhere, or anywhere can go to AJ. Okay, so that's normalized one. And also you can use random walk, and you can use symmetric random walk. Symmetric random walk means you random walk from AI to AJ, and you're also thinking about it from AJ to AI. Okay, then you try to add them together. Two directions, add them together. That's a symmetric random walk. Okay, so we just use this to see which measure is better, or combined measure is better. Okay, so one thing you probably can see is you can use all the different pass count. You can use common neighbor. You can use homogeneous network, the pass count. You can use rooted pass count, and you can use heterogeneous one. But using the heterogeneous network, this red line actually is the highest one. Simply says you get the best result. Even you look at the you based on this is a high productivity, 2-hop, 3-hop. This is a low productivity. That means that some author generate lots of papers, some generate less papers. Actually, even you partition them from the very highly productive authors or not high productive authors. No matter what you try to predict their co-authors, you probably see the heterogeneous one in every partition. You get the very best results. That implies we really should chase heterogeneous networks instead of homogeneous one. The homogeneous one may not give you the right answer. Okay. And then you look at the measure. The measure, which measure is better? Actually, the interesting one is if you look at we use like a pass count, normalized pass count, or random walk, or symmetric random walk. Then no matter what, you perceive the hybrid one is always the best. Okay. Of course, the second best is normalized pass count. It simply says we see those so many measures, but all these measures are reasonable. But finally you combine them together, in a hybrid way, you get the best result. Okay. It simply says what is the best measure? Actually, there's no single best measure, but of course, the normalized pass count overall is not bad. Okay. But the most exciting thing here is you look at the real prediction. Okay. The real prediction, the first important thing is you look at which paths finally give you the real good result. Okay. You check this path based on logistic regression, you calculate, you get a p-value. And anybody knows statistics knows this p-value, the smaller the better. Smaller, the sharper prediction. Okay. So you can see which one is the smallest one. You can see this AP-VPA, VAP-APA, and AP, this is citation. If you look at these terms, you probably see these 1, 2, 3, 4, we mark as a 4-star pass. Okay, these 4-star pass you see is either they share common venue, or they share common author, or they share common terms, or they share common citations. That means you probably can think about it, even you sit back and think about it, what should be the important things to judge whether these two people will be co-authoring in the future. Either you have lots of common terms in your paper. That simply says you're really talking the same thing. Or you all cite the same set of papers. Or you all go to the same conferences or submit papers to the same conferences. Or you have common co-authors, right? So in that sense, these several paths actually, even you think about it, sitting back and think about it, these are most important paths. The p-value is very, very low, very high. That simply says this is nothing. You should not use it. Why you should not use it? You look at this. You can see this one says, I got this paper. I authored this paper. This paper cite another paper. The other paper cite the third paper. Okay. Then that's the paper of the third paper's author. That's pretty far. You think about it. You cite a paper. That paper can cite anything, right? And they cite those papers. Those paper author is nothing to do with you, right? So that's why you try to predict you will be co-authoring with the other guy. It's too far away. Okay? Unlikely you are going to co-author. So that's the reason you look at this result. Actually, it's a very much match our own intuition. Okay. Then with this pass, you try to do the final prediction using these hybrid measures to try to do final prediction. Actually, we did it a lot. If you go to the paper, there are lots of real name, like even the student predicted me, who will be my co-authors from 2002 to 2007. Actually, it's reasonably high quality. This simply says, I know all these authors. I actually may have good intention to work with them. Okay. The magic thing is she picked up Jan Pei, who actually was my earlier student, graduated from me in 2002. And she predicted, because in 2002, he got a PhD from me. Then she actually predicted 2003 to 2009, Jan Pei will work with who will be his new co-authors. Okay. Then she predicted top 5 for these 5. Okay. Some are big names, like Philip Yu. Everybody probably worked with him, so it's nothing strange to predict him. But the other co-authors, some you never heard of their names. But actually, it really happens between 2003 and 2009. They do have co-authors. Okay. There's one prediction, Osmer Zayan. Actually, it's very high quality prediction, but it happens, it's wrong. Okay. So that year, actually, Jan Pei was the conference chair of KDD. He was sharing my keynote speech. During the conference, I actually, facing many people, I was asking what happened. Why? Because Osmer was my student as well. Now he's a professor in University of Alberta. They two both were graduated from my group, and both are professors in Canada, actually nearby 2 provinces, Alberta and British Columbia. I said, why you don't collaborate with him? You two must have some problems together, right? Why you don't collaborate after graduation? And he actually raised hands, said, because you can't until 2009. Actually, we got a paper in 2011. If you check, DBRP, we do have a paper. So that simply says our prediction is not bad, right? At least we predict there's a high potential they're going to have a paper until 2009. Even it's not 2009, just 2 years apart. Right? So I did check. Even I went back and checked it. They do have a paper in 2011. Okay, so that simply said that the prediction was not bad. But if you look at the other prediction, like you just use the shared common authors, you can predict Philip Yu and Jeffrey Yu. But in the middle of those people, they predicted actually it never happened. Okay, so that simply says just based on a common co-author. Co-authors will be co-authors. Actually, it's not quite right. People can see that. But you really need a heterogeneous network rather than homogeneous one. Okay? So that's why actually there was one person interviewed here from Stanford. Actually, I was challenging her and say, you look at this result, you use co-author, try to do prediction. We did it. It does not really happen, right? It did not really happen. I mean, you did predict a few, but many of them you predicted wrong. Right? Then after that, after her 2011 paper, she actually got another bold idea, said, not only I can predict co-authors, whether in the next 5 years you will co-author with somebody, she actually said, I probably can even predict about what time you're going to co-author. Okay, that's pretty tricky. And she actually relaxed a little. She said, I will predict at what time you're going to cite that author. For example, if Philip Yu got a paper, you never cited his paper before. Around how many years you're going to cite this paper, okay, in your authoring history. Okay. That means she wants to predict about when things may happen. This is a pretty bold goal because you try to predict yourself about when I'm going to go somewhere. Actually, it's very hard for yourself to predict. But she says we have lots of data. We have, like DBRP, you have all the computer science people's publication activities. Why we cannot predict? Okay, and what her basically saying is, if you look at the citation, everything you can map them based on the time. Like this is the time, 0.5 years, 1 year, 2 years. You can get this. Then you can write down all those functions. Then you may be able to derive the parameters for this y-bar function. Simply says you're going to see, based on the past data, what will be your functions on your citation activities. Then, based on this, we may be able to do the prediction. Okay, but I'm not going to give you the very detail because this is a very sophisticated statistic model, which just published in Wisdom 2012. People really like it because nobody dared to predict anything happen at what time will happen in the future, right? She actually worked out is based on the training. She partitioned the data sets into like this is t sub 0, this another period t sub 1. Then you can use this one train. You will be predicted another similar time slot. Okay, you can say this is the training, this is testing. After my testing, I'm going to predict the future one. Okay, so that's a one. She actually predicted pretty good. If you look at this, she predicted Philip Yu, who is a very productive author. He got like probably 700 or 800 papers in computer science. Predicted his paper when, though, about how many years later are going to cite this new author. Simply says this new author is based on Philip Yu's past history. He never cited those papers, so those authors. And she's going to predict about how many years, like likely Philip Yu is going to cite those authors. Okay. That's interesting. Then, based on similar philosophy, that means based on the heterogeneous network, she worked out these are the top-ranked metapaths. Okay. You probably see these top-ranked metapaths is completely different from the co-author metapaths. Only the first one maybe looks the same. All the others are different. Why? Why they are different? Why those quality metapaths are different from the co-authors? Simply, if you read those paths, you probably can sense why. Because citation is different from co-authoring. You think about that. Co-authoring, you must know this person you co-author, right? Citation, you don't have to know it. You don't have to know that authors, where they are, how, whether they're still alive or not. You don't care. Okay. What you care is the first important thing is topic. You work on this topic, you're going to cite paper in the same topic. So these terms very important, right? That's you probably can see. The second one is you work out a paper. If this paper, citing, this is co-cite the same paper. You think about this. Sometimes I myself sometimes also do that. Is I work on this topic. I look at other people's cite which papers. Okay, because if they all cite that paper, it simply says that paper is important. Then I probably will read the paper. Then we'll see whether I should cite this paper. Because if other people are working on this topic, they all cite this paper, you don't cite it, you probably never pass the review, right? They say you even do not know the paper. How could you work on this topic? So this is the citation. Okay, this is a follow co-author citation. You co-author with this. The co-author often cite this one. You probably also cite this one. And this one is this path length is very long. She derived. This is follow the citation of authors who study the same topic. So that means you got the same topic that's author, even you are not co-authoring with that one, but you work on the same thing. Okay. If they cite that paper, likely you are going to cite as well. So you see, this is very obvious. So you can see the top-ranked metapaths she derived based on the data sets are very telling. You think about your citation behavior, it's a similar behavior, right? Other people all work on this side of the paper, you're going to cite as well. So she, based on this, actually predicted, you can see some prediction are very, very telling. Like said, Philip Yu cite Lin Liu, okay? It said this is the median is 2 years, mean is 3 years, actually 1 year cited, okay? And this one, like a Christian Jensen, if you look at this one, said the median is 2.7, the mean is 4.29, the ground truth is 3 years, cite this author, okay? Of course, there are some, you probably see, this means never cited, okay? It simply says, like this one said 8 years or 12 years, but this one never cited. This actually is, some predicted, like a short time, but even 9 years or more, it just got cited. So that simply says, not everything you predicted can be true, but there are some very quality predictions, even on about when the first time you will cite a paper. So it simply says, with the heterogeneous information network, you get all the information into the network, even for the future prediction, something even you like an author, you did not even know it, but you may be able to predict those behavior, right? So it's pretty interesting. Yeah, this one is still in Northern Europe, in Norway. This is a harbor city. I think it's called Gothenburg. It's a little north of Copenhagen. Okay. Let's look at the remaining two things. Okay. Using heterogeneous information network can do something pretty magic. One is we set a relation prediction. You can see predict the co-authors. You can do prediction. But in industry, a lot of people want to do recommendation. I think most people probably know what is recommendation system. Okay, recommendation system essentially is, for example, you got a movie. Okay, you watch a movie, your friend watch a movie, or some people watch a movie. Sometimes you may give a rating or something. Then the recommendation system may say, even you did not watch this movie before. They will show, if you watch this movie, likely what will be the rating. Okay, that means they make a recommendation. This actually is very important because you think about it on a web page. If you serve the web page, they give you the links, say, oh, likely you're going to buy this thing. They put things in, you click the button. Actually, for you, it's very convenient because you think, oh, the website even know what I'm going to buy, right? So I click the button, I want to look at it. For the internet company, this is their lifeblood, okay? Because how those advertisement company are going to give you money is you put this one in the right place, right customer. If the customer click it, the advertising company are going to pay Google, pay Yahoo, those money. You say Google, Yahoo, or Facebook got so much income. Where the income come from? From the ads, essentially. Okay. So for them, they devote a lot of money, time, work on these recommendations. Because you put the right recommendations, the people are going to click, they got an income. Otherwise, the Google will do everything for free, right? Because you don't pay by surfing Google, you do not pay anything. Okay. Who will pay it? Those advertising company will pay it. Okay. So then we look at the recommendation system. What could be the problems? Okay. The recommendation system, if they collect a lot of data about you, like your traversing history, weblogs, they can make a reasonably good prediction. It's just like if you watch a lot of movies, okay, you give the movie a lot of ratings, then they may make a good recommendation because they know what kind of movies you really like, right? But the problem, the most problem actually is in the long tail. the data they collect about you is very, very small. Suppose you did not use like Google or Yahoo so popularly. So they collect very little data about you. Another very important thing is you get a new movie. Suppose they do not collect a lot of history. Who is really like this movie, right? They don't have both ends. That means they don't know much about you. They don't know much about the movie. That's a hard time. People call this a cold start problem. Because once you start, you become a familiar user of the web. And the movie become very popular. They know what kind of people like what kind of movie. Then it becomes easier because they collect lots of data. Okay, that means if the data is around this, from the power law point of view, it's around those, power line. Okay, you get lots of data, then it's easy to predict. The problem actually is the long tail. Long tail means you get a very few people, especially a new movie. You get a very few people give you the history, and you do not know even the user. Okay, how could you make a prediction? That's a problem for a lot of recommendation systems. They call this a cold start problem. Okay. But the interesting thing is everything is networked. If you think about this, you got a new movie. For example, suppose you got Avatar, okay? Avatar, suppose, just came. But you know Titanic, you know Aliens, you know Revolutionary Road, you know lots of previous movies, okay? Suppose Avatar just came. You do not know yet, okay? How could you make a prediction? You based on the features of this movie linking with all the others. You think about it. If this movie was, say, directed by the same director as Titanic, okay? Or you have something like a science fiction or something. So you get lots of features there. Then you probably will be able to make a good prediction. You say, oh, this person really like Rob Cameron's movie, so this is another one, then I make a prediction. I make a recommendation, right? Or this one guy really like some very interesting science fiction, maybe Avatar is one of them. Okay? So you can see this. Another thing is even you may not know these people, but you may know his Facebook friends. He get lots of friends. If his friends really like science fiction, maybe he likes it too, right? So they use social networking can do prediction. So the interesting thing is you have to use heterogeneous network to do this. Okay. So that's the general philosophy. The philosophy was we have to do personalization as well. Okay, like here, you see there's a data level, there's a model level. Okay, if you get this aliens, if they say, oh, this guy is a Cameron's fan, this guy is 1980s science fiction fan, or something, then likely will like this movie because you have the old history. You may predict the new one. Okay, so then this one is you can even thinking about the network is not a purely like simple Facebook. This network, you are looking for the heterogeneous network. Heterogeneous network in the sense this is the movie. And these are the people linking with movie. These are the people may link with other things. So finally, you may be able to find, using heterogeneous information network, you're going to do good prediction. Okay. So the general model, this paper was another student, Xiao Yu. He worked together with Yi Zhou Shen, got this paper. Xiao Yu, after he got this paper, actually, Google really liked his paper. Google actually recruited him to Google Research. He actually is working in Google Research now. You probably can see the recommendation. You probably can see also any company, any internet company, no matter Google, Yahoo, Bing, or Baidu, all these, they actually recruit lots of recommendation system people because they really want to do good recommendation. Okay. So if you look at what his proposal is, you get a global recommendation model and a local called personalized recommendation model. That means you, based on the general features, you try to construct a global model, like what kind of movie and what kind of features they link together, you can make a good recommendation. Okay. This is most people probably can think about. You use heterogeneous network, you can construct this global model. The second one is personalized recommendation model. That means if you recommendation without thinking about this particular person, because this person may be somehow different from his friends or from something, you want to see the personalized model. But how do you see personalized model? The general philosophy is the user, you try to group them based on your behavior, group them into clusters, compute those clusters. Okay, so you can see this one is you have user, you have item. Okay, this is the I is actually user, the J is item. You based on user item, this is transpose matrix. You just compute this matrix, right? These are the parameters you can derive. Okay, this is then finally you can get right ranking score, but that's a global ranking. You try to get a local ranking, you need to look at this user actually are putting into different clusters. That means you need a clustering algorithm based on the past history. Based on the heterogeneous network, you try to find the user clusters. Okay. For each cluster, you can derive their model. Okay. So this is basically you have a global recommendation and local recommendation. Finally, you integrate them together. Okay. But I'm not going to derive the detailed one. The detailed one essentially is you have an objective function. You try to minimize the loss based on this objective function using some kind of sigmoid function. But I'm not getting into detail on these formulas. But the general philosophy is use heterogeneous information network, use this information, and use a little sophisticated model, and use personalize the clustering, and using these several things getting together, you are going to derive the model. I just show you the result. You probably can see why this is pretty interesting. Okay. What he did is he used two big data sets. One is IMDb. IMDb is a movie database. It really gave you lots of features on the movies. Another one is Yelp. The Yelp, that's also, very popular. You get different items, different users have different ranking on these items. You probably can see his information network contain like a Yelp contain, 11,000 items, 43,000 users, 229 ratings. Just these are all pretty big data sets. And he used these two data sets and then look at all the previous algorithms, try to compare with them. For example, there are some algorithms based on popularity, some based on co-click, some based on non-negative matrix factorization, which is very popular, some based on hybrid SVM algorithm. And he has two models. One is heterogeneous network global model. Another is heterogeneous network local model. So the personalized information essentially is this local model. That means not only you derive the global formula, but also you derive the personalized clusters. And if you look at these formula, you can see, if you look at the top recommendation, the precision 1 or 5 or 10, you can see his model always get the best result. This is a mean reciprocal rank. It's based on the ranking, and he also get the best results. This is more like IR ranking, okay, information retrieval measure. But no matter what, you can see his method always get, comparing with other rivals, he always get the best one. This is good for the data. You do not have much data. You have a cold star problem. You use network information. Right? You can get a good result. Okay. So that's the one. This one is you probably know the Little Mermaid. This is I visited Copenhagen. Copenhagen they put this one as a symbol of their city because that's the one The author is Hans Christian Andersen. Andersen is their pride because you look at so many, I think, so many famous ones. It was like authored by him. Like this Little Mermaid. This there are many, like Seven Dwarfs, or there are so many famous ones authored by him. So the Copenhagen, Denmark people really take him like it's the most famous wine in the world for Danish people. Okay. Then I'm going to introduce you another very interesting paper. Actually, was done by the current student Xiang Ren. You probably will study quite a few of his papers. This one is use heterogeneous information network to do citation recommendation. Okay, this is very typical for us. Like you work out a paper, you want to submit to a conference. Sometimes you want to check whether your citation is good. Because if you do not cite good related work, very likely those reviewers will not let you pass. Right? They say, you even do not know this work, how could you do this newer ones? Okay, most people actually rely on the previous studies. They did something quite good. You say, I can even compete with them. That's why you can get papers published. The citation recommendation is very important. Actually, after he published this paper, even some Google people contacted me and said, oh, can you really implement this one as one of the functions? Google may even want to host it. Okay, because to do the research paper citation is a very tricky thing. Everybody want to get. But of course, we finally did not really put it into Google. But if anybody interested, you can continue work on this. You can get a production function. Maybe Google will really be interested. The general philosophy is this: suppose you write a paper, a research paper. Okay, you are the authors. Suppose you want to submit to a KDD conference. And you have these terms like topic modeling, information networks, Gibbs sampling, all these terms. Then the question becomes what papers they are going to recommend. The system is going to recommend you cite. Okay, that means they will give you citation recommendations. So you should cite those papers. Those papers are important. Okay. Can we automatically generate this ranked order, say this is most important paper, second most? These papers you should cite, you can check. I think it's very valuable. That's why the Google people actually talk to me in the conference. So they are very interested in this paper because it's very useful. Okay. Then we probably can give you, this one was published in KDD 2014, led by Xiang Ren. That I think the first two are still in Jialu Liu. They're still in the PhD program. Xiaoyu already joined Google Research. Urvash already joined Stanford for PhD. Okay, and Chen Tiangu already become professor in University of Virginia. So those are several authors you probably see. They all get into good places. And actually, Jialu, his graduating, he already been hired by Google Research. Okay, so that he's also going to join Google Research. Okay. But Xiang Ren is still probably next year will graduate, not this year. Okay. So let's look at what kind of thing you should consider to recommend citations. Okay. If you look at the previous work, some is just based on they call content-based or context-based. That means you just look at you have these words. By the context, you should cite something. They will give just based on the word. You look at the up and down a little what you're discussing. They will recommend you what to cite. Another is topic similarity based. Topic similarity based means if you work on this topic, suppose you say I'm working on deep learning. Okay, this is topic. Then they say, oh, you're working on deep learning. These are deep learning papers you should cite. This is topic similarity based. Okay. Another study is a structure similarity based. Structure similarity means you probably want to submit to this conference. you probably cite those famous authors because those are the dominating authors in those venues. So another one is a hybrid method. They try to mix this. Everybody give certain weights, okay, then hybrid them. Okay. So, but if you think about the real thing, in this, actually it's a pretty complicated thing. Just thinking about this. Suppose you got a paper. The paper is discussing called recommending citations for academic papers. The other paper said supervise the random walks. This is a precision recommendation links, predicting and recommending links in social networks. Suppose you get these two papers, they have certain keywords. Okay. But you can see there are some common keywords, like this paper may have link prediction. This paper also have link prediction because you have predicting links. So you also have a link prediction. So it's just based on the words you try to work out these, you can write down a few keywords. Those are the information networks on the interesting groups. But you can see some people, for example, you may say, for this problem, maybe LeJAR is an important one, or maybe literature search is important topics. But you have to think about there are authors, there are topics, there are venues you want to submit, and there are keywords. So all these are actually belong to different components of information networks, right? Like a KDD is a venue. You submit to KDD, or I submit to SIG-IR, will be different because KDD is a data mining conference, SIG-IR is IR conference. So you likely will cite different sets of papers because the reviewers may be familiar in KDD, they are familiar with KDD papers. But you go to SIG-IR, they probably do not know that paper, they know other sets of papers. Right? So you need to know what are the problems, where you submit, who are the authors who are good on what thing. All these things should be considered for any citation. Okay? So that's the reason you can see it's a rather complicated problem. It's a joint problem. Okay? So if you want to solve this problem, you were thinking about this essentially is a heterogeneous networks. You have venue, you have paper, you have author, you have terms. And within this network, you try to build up a citation model. Okay? So that means if you think about the problem, you can formalize like this. Suppose we have a bibliographic network. That means we actually have lots of papers, terms, authors, venues, they all already link into a big network. You know their citation behavior. This paper cites this paper, you know it, right? And now you get this network, you get terms, you get authors, and you get target venues. Say, this is the place I want to submit. I want to send it to KDD, okay? Then you have your own manuscript. That means you have the paper there, submit the paper to the system, okay? Then what we want to get is high-quality references. That means we will generate papers, say these are the top-ranked things you need to cite, okay? That means you finally give the paper, give a ranking score. Say this is 0.92 means this one probably is more important than the other one to cite, right? So then if you think about it, to solve this problem, the first important thing is we need to do certain clustering. You need a soft clustering. I actually did not answer one question from Piazza, but I read it. One student said whether you need to assign this one 100% to this cluster or only partially to this cluster. Okay, so actually you probably see our framework, including rank class, including this paper, is soft clustering. Soft clustering means you do not say this one is 100% going to this cluster, nothing going to the other cluster. Essentially, it's the distribution. It's a soft one. Okay. Of course, it may happen finally you compute it, say this one is really 100% here, 0% there. That's possible, but that's rare. Okay. Most cases, you may have a distribution. Okay. So you want to softly clustering into different interest groups. based on these heterogeneous network structures. Okay, that means you need to do the clustering, then you need to derive this query, this manuscript, belong to which cluster, belong to which group, how much it belongs to, right? Then you need to judge the relevance, you need to judge the authority of the paper. Not every paper on site, only good paper on this topic on site, okay? What are the good papers? The good paper could be published in reputable venues, authored by some famous authors, but cited many times, or something like this. These are the authority of the papers, right? So you need all these together. You finally have an integrated model. Okay, then you can do good recommendation. Okay, then you look at this one. The first thing you want to look at is for this citation, you want to check this is the query, this is the paper you want to cite. What are the scores? Okay, and the score actually is a summation of these several factors. Okay, one factor is for this query Q, which group it belongs to. Because you belong, suppose your one is on recommendation systems, okay? So your query is recommendation system, likely you will cite the recommendation system paper. So they should be in the same cluster. That means you first want to check which group member this query is. That means this manuscript is a recommendation system paper, that's a group. Then for this group, okay, you totally have K groups. From 1 to K, you sum them up. For this group, you want to see, for this particular group, you want to see their relative citation score of the paper, and you want to see the paper's the candidate, essentially the relevance. You want to calculate the relevance, you want to calculate their citation score. Okay, then you can integrate them up, you can get the whole thing. Okay. Then how do you get this group membership? Getting group membership actually is using heterogeneous network. I can give you this one, you probably can see. Is if you want to check the relevance, you need to think about the heterogeneous network. You based on the known citation behavior. You are going to see which metapath is more important. That's a similar thing as what Ido's prediction paper, right? You can think about it, whether it's a co-author or co-term or co-venue or like citing the other papers or being cited by other papers. You look at those behavior, then you try to calculate the relevance and calculate the cluster as well. Okay. So you can see this one essentially is based on the relevance. Based on this, you can see different groups actually have different relevance scores. It's very interesting. That means for this kind of paper, something is more important. For the other paper, maybe the other metapath is more important. Not all the papers have the same metapath importance. You probably see. For group 1, this like a co-author citation is more important. But for this one, for this group 2, like a co-term citation is more important. And this group 3, you probably can see this one is a co-term and being cited by is more important. And group 4, you can see this is a co-venue is more important. So different groups actually, the metapath, which one is more important is different. Okay. So you calculate based on the cluster of the group, you calculate different metapaths. Then you calculate the relevance. Okay. So with limited time, I will not give you the very detail, but the detail I put a paper there, you can read the paper. But the general philosophy is this formula. Okay, the formula is a little more involved, but I probably just give you the general philosophy because Xiang actually used this philosophy in many of his papers, including the later you want to see the class type. Okay, this class type paper essentially is a joint optimization framework. What is joint optimization framework? That means he was thinking you have several factors important. One is relevance, one is a grouping, one is authority scores. All these are competing factors. Okay. What he did is he threw these competing factors, because it's a summation of these several things. He just threw them into an optimization framework. That means he basically using the optimizer. Okay. This is more like you probably got operational research, you know, it's kind of an optimization of several functions. He throw these functions in, he just call these optimization routine. Say, at what condition these different combination, different parameters combine together, I get an optimized score. That's the one I give you the best ranking. Okay. So he basically put these several models into this optimization framework. Okay. With this optimization framework, okay, he basically put this one into a loop. This is a little like, you know, we said EM, this kind of loop. You can see at the very beginning, he initialized this one. He gave the three things. You have paper, author, and venue. Okay. And the citation counts. It's just initialized based on this. Then he put this one into the loop, try to optimize the whole thing. That means you can update the group membership, update the feature weights, computing the paper relevance, compute the author authority, and compute the venue authority. You know, compute this, then you try to derive the score, then you go back again and you adjust them again. Okay. Then until it converges, means until I finally derive the optimized score. Okay. So then after that, he can give you the recommendation, what is the best papers based on his computation. Okay. I probably can show you what he did in the real test. You can see he used a pretty large data sets. For DBRP, he used 137,000 papers and 2.3 million relationships. These are the average number of citation per paper is around 5. Okay. For PubMed, which is a medical publication, which is even bigger data set, he actually also used 100,000 papers, millions of relationships, but the average paper citation actually is larger, it's 17. Okay. Then you can see he used a year is from DBRP is like 1996 to 2007, and then the training year for PubMed is 1966 to 2008. Okay. Then he wants to test the real one, like for 2009 to 2011, he wants to test those papers, his citation model, whether he can predict the right one. That means he predicted those cited paper, look at the real cited paper, how much may match. Okay. And these are the metapaths he has been using. He used a PassSim and a random walk-based measure, okay, both to do the testing. Okay. There are several interesting things. One thing is he predicted the top-ranked venues and top-ranked authors for particular field. For example, this is for database and information systems. He predicted these are the top-ranked venues. These are top-ranked authors. And for computer vision and multimedia, he predicted these are the top-ranked venues. These are top-ranked authors based on the citation. Okay. And another interesting thing is you probably see the citation, the venue does play an important role. You can see this group A likely are the database group. You can see what venues they cite. They cite sigma VRDB very high, you can see. But on group B, they don't cite those papers. They cite TPAMI, is IEEE transactions on pattern analysis and machine intelligence. This is the AI one. This IJCV is International Journal on Computer Vision. Okay, those are the pattern recognition and vision people. They don't cite sigma VRDB much, but they cite this part a lot. That means really different groups, they cite different sets of papers, right? Another thing you can see is for the same group, okay, the group actually they cite Philippi and Rakesh Agar a lot because Philippi and Rakesh Agar are in this sigmod venues, okay. But if you look at group B, the same group, they cite Thomas Reps and Ken Kennedy a lot. These are the people in this group, in the pattern analysis group. So you can see they cite different sets of authors. So that means different groups, they do have very different citation behavior if you look at the venues and the authors. Okay. Then, of course, the important testing is what are comparing groups, like whether you compare with the others, whether you can win. And he actually shows, you probably can see that the last number is his class site. And the next one is a class site only use a relevance score. And you can see almost everything here in DBRP and PubMed, his citation model is the best. Okay, so that shows actually using heterogeneous network model really can do a lot of interesting things. So I think I finish, this set of slides. We do have one student presentation. Okay, I think I'm going to load the paper so we can use the last 10 minutes to have this presentation. Okay, the presenter is Xinlu Liu. Okay, so. Xinlu, you can come up. You can do the presentation or pass this one to you. Okay.
Thank you, Professor.
So you can introduce yourself and introduce the paper where the paper comes from.
Yeah. Thank you, Professor. Good morning, everyone. Today I'm going to introduce a paper focusing on how to automatically generate metapaths in large heterogeneous information networks. It is written by Dr. Meng, his group, and it is a recently published paper. It's just published in 2005 in the International Conference on World Wide Web pages. So that's a quite new paper. And it is quite interesting because in our courses, we, especially this past few weeks, we primarily focused on how to apply the metapaths that is already established by the expert in the database system to calculate the similarity search and also give the recommendations to the users. However, this paper is talking about how do we generate those metapaths not manually but automatically. So this is an introduction. So in this paper, I will use HIN to represent the heterogeneous information network. And currently, it is widely applied to calculate the relationship prediction and similarity search in large and complicated data sets, for example, Yago or other knowledge-based data sets. So current problem the paper would like to solve is how to obtain the metapaths. Just like I just said, right now people are using the manual retrieval. So it's like in the bibliographic data set, we use like the paper venue paper or paper co-author citation paper, something like that. We got a metapath by ourselves already. However, it may not work for some large data sets. For example, Yago, because it's, the paper majorly talked about it. The knowledge are linked together. It's not like we know how they linked. We don't know. So, however, if you pick the pairs, for example, we can use the example here. Mr. Obama and Lady Obama, we know these two people are related. So we may not know which metapaths linked them together, but we know they're related. So using this algorithm, it can automatically generate the metapaths based on the example pairs given by the users. So here is an example about how to use the path count to do similarity search. So here is a graph of the US president candidate in last election. And we know, as people we know Mr. Obama and Ms. Obama, they are strongly related together. But assume we don't know, we just run through the algorithm and it will generate 3 metapaths automatically. And by counting those metapaths, we will notice that these 2 people shares the most paths together. So we know they have strong similarity. We know they are strongly related. So that's how this how this algorithm will work. So let me introduce. Let me make a comparison between their previous works and their proposed solutions. This graph is really important. That's the backbone of their paper. So in the past, the metapath is provided by the domain expert, and usually they can only have paths that have a fixed length, so they cannot exceed a certain length. But this may not be helpful in the complicated hierarchical relationship. And in this paper, they compared their algorithm, which is called FSPG, forward stage-wise path generation, with the existing method. It is called AMI. So it concluded that the FSPG has an improvement in accuracy and is more scalable than the current method, and it can be customized because the pair generated by the algorithm could be reviewed by the users. So if the pair actually it's statistically relevant, however, it's not really relevant, the user can just eliminate this pair. So it increased the accuracy of the metapath. So that's how it works. First, there will be an example pair, node pairs given to the algorithm, and by the first stage, it will generate the metapaths, which will include new mode pairs, and those pairs will be suggested to the users. So users have a chance to review them, and they can either accept or reject the pairs. If it is either accepted or rejected, there will be a new node pair generated, and this will repeat until the residue value of the pair generation reaches 0. So here is their math models to describe the HIN models and metapath models. So we can skip those words here, but there's 2 very important things here. It's the similarity function and the similarity aggregate functions. The similarity function is based on the random walk, so it's like it is counting the similarity between 2 nodes. So it is counting the probability from node A working to the node B. If the probability is high enough, then they're similar. And by the aggregated function, it introduced the metapaths into it. For example, let's use the Mr. Obama and Madam Obama, for example. This shares quite a lot of metapaths, as we saw in the introduction slides. In this way, due to the shares, due to the random walk generator score, that means from Mr. Obama can easily reach Madam Obama, and also they shares quite a lot of metapaths, so they will score very high in the similarity aggregate function. And that's the algorithm about how to generate the metapaths. So we are given a network, and we have the user to give us the example pairs, and the output will be a complete metapath. And R is residue values that will reduce in each iteration, and the W is the weight of the weighting vector of the path, and the K is number of the passes. So there will be a greedy tree method that will be introduced in next slide about how to generate each new node pair. And in the initialization, the path and the rating will all be 0. And in each iteration, when the residue value is larger than it is not neglectable, the path will increase by 1, and there will be node pairs generated by the greedy tree method. And the node pair will be put into the existing path, and there will be a correlation calculation based on the node pair and the residue value, and it will be compared to the threshold that is given by the users. So it's like at the step 8, it is reviewed by the users. And then the U and gamma, U is the direction vector in the stage-wise metapath generation, because this is a forward algorithm, so it will only point to the next one. It will not go back. And the gamma is the step size, so it will you can say how far you would like to go in a metapath. So it will so in step 10, the residue value will reduce and the weight will increase. So slowly the residue value will reduce to 0 or a negligible value, and then the metapath will be generated. But if the iteration went too long, it will automatically end in 50 stages. And this is a greedy tree method, and it is quite straightforward. We can see there is a priority score on each iteration, and only the largest one will be left to be collected. And I will quickly go through the experiment on Yago with the comparison with AMI and other random walk method. So we can see it always scores the highest, and it can also discover the unnoticed metapaths that AMI cannot find by themselves. So in conclusion, the FSPG is better than other current methods. So yeah, so that's their work, and I think that is really fabulous. So thank you for to hear my presentation.
Actually, this one is a very good paper. It's a very important direction. Okay, not only this one paper. After we got so many papers, recent trend, because you probably can see what we did is we took a DBRP, IMDb, YERP. Those things are very tiny schema. If you look at schema, you just get 5 or 6 objects. They link together. And then people realize if you go to knowledge base, like DBpedia, Freebase, Yago, or these, they got thousands of different objects, got a very big schema. So finding metapaths, constructing this metapath become a very important problem if you want to use this model. That's why you probably see this, Shinlo actually got this paper, and there are quite a few new papers recent year, all work on this. That means work on metapaths in a very complicated schema. Okay, if you want to do research, you move that direction, likely it could be very fruitful. Okay, thank you.